Using the Bronsted-Lowry definition, we defined an acid as a proton donor. So here acetic acid donates a proton to water, and that yields hydronium. And here H2O is the base because it accepted the proton. And here you have the conjugate acid-base pairs, whereas the acid loses a proton in a forward reaction, and the base gains a proton in the backward reaction. And here is a similar example, where H2O acts as the acid in this case, by losing a proton. So effectively water is amphoteric, because it can act as an acid or a base. Now we can write acid-base reactions in a shorthand form. So here we have hydrochloric acid reacting with water to produce hydronium and chlorine ions. And here is a shorthand notation where we omit the water molecule. So these mean the same thing. So the hydrogen ion and hydronium ion are often used interchangeably. And to measure the acidity of a solution, we take the pH, where P of a certain value generally means minus the log of that value. So pH means minus the log of the concentration of hydronium ions, and pOH in a similar way means minus the log of the concentration of the hydroxide ions in the solution. And we'll explore these further. Typically, the concentration of hydronium in an aqueous solution ranges from 1 molar to 10 to the negative 14 molar. So if you take the log of these values, you get the range of the pH being from 0 to 14. Now sulfuric acid is an example that falls out of this range, which is also known as battery acid, and vinegar has a pH of around 3. So the pH of acidic solutions is less than 7, and basic solutions have a pH greater than 7. So ammonia is a base which has a pH of around 12. So the pH scale is convenient because typically you get concentrations of hydronium being quite small. So for example, in water is 10 to the minus 7 molar. So if you take the minus log of this, you'd get a pH of 7 for fresh water. And pOH is a similar concept, which is basically the minus log of the concentration of hydroxide in a solution. Water is amphoteric, so it can act as an acid or a base, and it can therefore self-ionize or autoionize, where two water molecules react to yield hydronium and hydroxide ions. And the equilibrium constant for this reaction is 1 by 10 to the negative 14 at 25 degrees, which is temperature dependent. So now we can write this equation using the concentrations of the hydronium ions and the hydroxide ions, which have stoichiometric coefficients of 1 in this balanced reaction. And this is equal to 1 by 10 to the negative 14 at 25 degrees. And we can take the negative log of this entire equation, so this term becomes 14. Then using the rules for logarithms, we can break this log up as follows. and therefore we obtain the following expression. And that's applicable at 25 degrees. So in pure water, the concentration of hydronium and hydroxide ions is the same. So if you designate them both as X, so you'll have the following expression. And if you take the square root of both sides, we obtain 1 by 10 to the negative 7 molar, which is a concentration of hydronium and hydroxide in the solution. So therefore, the pH is equal to pOH, which is equal to 7 in a neutral solution. As we've seen, the equilibrium constant is temperature dependent. So in the autoionization of water, which is an endothermic reaction, so we add heat to the reactant side, and therefore an increase in temperature would cause a shift to the right by Le Chatelier's principle. And consequently you get more products being formed, and the equilibrium constant of water will increase with an increase in temperature. So we can see that when the temperature increases, the pH and pOH decreases, because the concentration of hydronium will increase, and so will the concentration of hydroxide at the same time. So consequently, water remains neutral at different temperatures, and therefore the following relationship still holds, where the concentration of hydronium and hydroxide ions are equal, so therefore pH is still equal to pOH. Except this term here will be different, because the equilibrium constant is different under different temperatures. The pH of a solution of vinegar is 3 at 25 degrees Celsius. Calculate the concentration of hydroxide ions in the solution. Well, we can use the following relationship to find pOH, and recall that the equilibrium constant at 25 degrees, and substituting for pH, we can obtain pOH. And that's equal to minus the log of the concentration of hydroxide ions in a solution. And solving this gives the following result.